could have hoped for was a career in geology. A few people that are no longer with us were instrumental with what I had to do. Harold Dreves, Pete Peterson, Ralph Roberts. Ralph came out to my thesis area and gave me one of the most encouraging things I've ever gotten. And that was, he said, Chuck, don't ever hide under a bush. Talk with people about what you're doing and see what they can help you with, because in the long run, you'll gain a lot more than you lose. And I've tried to follow that, and I think he's really great. Another couple of guys, J. Fred Smith with a survey, and Ed DeWitt, no longer with us either. And then some of these clowns that are still around. Larry Sneeze on there, Earl Brooks isn't, Connie Nutt, Barney Poole, Paul Emsbo, Keith Howard, Art Snoke, Sig Snelson, who was the first guy out there, George and Davis and Greg Davis, not brothers, Harry Cook, Mike Gressel, I hate to mention him and Harry and Chris in the same breath, I don't know if it's fair to them, but and Steve Reynolds and Andrew Zouza. It's been a hell of a run, and I couldn't have asked for a better time in my life.
I'm glad he had a good first.
So here we go. Let's see what happens here. Is that the way it's supposed to be now?
No, can you switch it to the other view?
Oh, yeah. Like that?
Indeed.
Yep.
Huh?
Yes.
Okay, yeah, you didn't want to see this other stuff. But the regional tectonics based on the Pequops and the Wood Hills has had me intrigued for decades. And I was a lot lucky, I think, to get back into it late in my career, or in my withering years, or whatever you want to call it. But it's been a ball this last 6 years working with this crew. And what we've come up with is really some more than I had expected, but it is what I had hoped. And I'll relate that as we go along. But first of all, we're going to be talking about the Ruby East Humboldt complex. So what the heck is a metamorphic complex? Well, Peter Coney, back 4.5 decades, defined it. He was down at the University of Arizona, and he defined it as a metamorphic complex in the core of an orogeny, not the core of a mountain range. And some people, I think, still don't quite comprehend it. But it's much more than one or two mountain ranges. In Nevada, it incorporates quite a large area for the Ruby East Humboldts. As a result of Peter's work, geologic ideas in the Western North America were turned upside down. Core complexes became the hot topic. A GSA Penrose conference on core complexes was held in '78. That's 1978 in Tucson, with a little over 80 geologists there. After that, the race was on to the Great Basin. Peter was the man who started one of the biggest bandwagon effects that ever existed in the geology of the Basin and Range. People were jammed in that bandwagon like sardines, and we all worked together. I feel very comfortably and safe for a cause. It was an exciting time, and it still is, but not quite like it was in the 70s to the 90s. Graduate students and their professors were out there like flies on garbage. You couldn't go to a place where there was somebody talking about a core complex. But one of the biggest and most poorly understood questions was, how did those complexes get buried so bloody deep? And again, how did they come up so fast? Well, from my perspective, which you will hear tonight, is that they perhaps weren't buried so darn deep originally, and therefore they didn't have to come up so far so fast. One of the great sports about geology is making progress, and hopefully it's positive progress. Now, a few of the early characters before the complexes were even talked about. This guy, Sig Snelson, he's online now. This is him in 1957 when he worked in the Northern Rubies and the East Humboldt under Peter Misch. At that time, if it was a crystalline rock complex, metamorphic complex, it was Precambrian. And all he knew was it was a complex area and the metamorphics had to be Precambrian. And he broke out, though, very importantly, two different suites of rocks, the crystalline rocks and a metacarbonate sequence. And that kind of set the scene. And later, Peter sent me down there in 59, and Keith Howard came in from Yale in 66, and we started tackling these interesting areas. And then this guy, Dick Armstrong and Art Snoke came onto the scene. These five guys were out here before metamorphic complexes existed in our vocabulary. We just had a great time wandering around in the wilderness, mapping what we saw. And we went at it with a vengeance so we could get our thesis maps done and get the heck out of graduate school. But the geology was so different and exciting, most of us have come back and had a ball. We jumped on the bandwagon and haven't learned yet how the heck to get off of it. Peter Coney was the leader of a fantastic program. And did he ever fill the wagon? Primarily, it was academia, but a few survey people were intricate parts of it. University geological surveys, which I refer to as, came out of the woodwork. University of Arizona, USC, Stanford, University of Wyoming, Yale, and San Diego State had the bulk of the students out there working. All of a sudden, there was a massive attack on these metamorphic core complexes. Little did we know that more than 45 years later, core complexes would still be a hot topic on most of the continents. Now, to get to the Ruby East Humboldt complex, what are the parts? First, there's a bad term, maybe the core, but the Ruby East Humboldt suite, which is a suite of Precambrian crystalline rocks that have engulfed a series of small percentage of regionally metamorphosed lower Paleozoic and perhaps Neoproterozoic rocks. On top of that is a myelinitic carapace. Some would call it a décollement zone, other would, more popular term now is a detachment zone. On top of that detachment zone is what I call the Wood Hills suite. It's a suite of metamorphosed and non-metamorphosed late Precambrian to Phanerozoic strata. And that's what we're going to be talking about tonight. First of all, where are these places? Well, this is a part of the Pequops that has been the top target that we've worked on for the last 6 years. Over here, the Ruby Mountains and the East Humboldts. This is the prime location for the Ruby East Humboldt Metamorphic Core Complex. But there's an upper part to that complex, and this is just part of it, but it extends clear out over to Wendover and beyond. All of these ranges out here are in my book what I call the upper plate, or the Wood Hills suite. So what we're going to look at is the upper plate, the suite metamorphosed and non-metamorphosed Paleozoic rocks, how they were buried, their metamorphic history, and how we can apply what we've learned there to the regional tectonics in eastern Nevada and western Utah. Now, back to this. The main emphasis is on the 6 years here in this area. The northern Pequops are underlain by the uppermost beds of the Neoproterozoic sequence, plus a complete Paleozoic section in this area. Beyond that, if you go on south, it gets into Triassic, and all the way down here to Curry, which is just below here, get into Triassic and Jurassic rocks. The youngest rocks involved are lower Jurassic Nugget Navajo, which when I was working out there, it was affectionately referred to as the Nugaho. Now, the problem that one of the big problems we came up against was that geobarometric pressures in the metasedimentary rocks based on metamorphic mineral assemblages have been interpreted to indicate that the Pequop section was buried approximately twice its normal stratigraphic depths, about 20 kilometers. This has led to the interpretations that the entire stratigraphic section, as we see it today in the Pequops, was duplicated by a theoretical 10-kilometer thick Windermere thrust sheet. Now, this Windermere thrust sheet was interpreted to have rooted over here northwest of the Wood Hills and come clear across the Wood Hills and over the Pequop Mountains, a 10-kilometer thick section of non-metamorphosed Paleozoic rocks being thrust over that in a southeastward direction. This was done to get the rocks on top of these metamorphic rocks to account for the geobarometry that the metamorphic mineral assemblages have given. Now the question is, where do we get off discounting the geobarometric data based on metamorphic mineral assemblages? We don't believe that thing happened. Quite simply, by doing detailed mapping and using a very simple tool called Conodont Alteration Index. You'll get to know more about these than you may want to hear, but they're critical to doing structural geology. Now, main points that we're going to talk about. The results of negating this Windermere thrust and its supposed burial of the northern Pequops and the Wood Hills. Second, what were the conditions in Northeast Nevada during Middle Jurassic to early Cenozoic as deduced from the geology in the northern Pequops? What about the regional metamorphism and southeast directed contraction deformation during the mid to late Jurassic Elko orogeny? This was the initial regional metamorphic event in the region during the Mesozoic. And then what happened in the region during the Sevier orogeny? Very hot topic. Now, just to put in a time and space idea, here's the Elko orogeny. It was a upper Middlezoic, upper middle Jurassic to middle late Jurassic tectonic event. On top, between that and the Sevier was the deposition of the Morrison Formation, a period of very, what we might call a very small lull in the sequence of deformation, but a very important one. Laterally and time equivalent to the Elko would be the Looning Fencemaker, and then the stuff over in the eastern Sierras. Now, to start off looking at the Ruby's metamorphic core complex and to understand the history of the Pequops, because the Pequops play an important role in the tectonics in Northeast Nevada, as well as the regional tectonics in Eastern Nevada and Western Utah in the Mesozoic and Cenozoic, we're going to look at a bunch of stuff that hopefully you'll enjoy. The interpretation of the setting of the Pequops from Middle Jurassic to early Tertiary is crucial. So, were the Pequops buried to twice normal stratigraphic depths as had been proposed? Or was the region never buried more than normal stratigraphic depths? Big difference. If the area was buried deeply, it implies about a 70-kilometer south shortening with thrusting to the southeast. If it was not buried, then one cannot use the proposed 70-kilometer shortening in constructing palinspastic cross-sections and maps. And this becomes very critical because people have been doing this for a while. And people who use that, there's no basis for it. And their data are not reliable. Now, a quote from a very good friend of mine, Mark Barton. Too often, comfortable answers, in particular geologic stories, seem sufficient. Partly too, because we have become tool-focused. The last decade, indeed the last century, has seen remarkable advances in the many tools applied to mineral deposits, and I would say all of geology, even though the basic questions and the fundamental applications have largely remained the same. With the newest results, it is easy to be superficial while ignoring the true complexities of an issue. Yet while state of the art tools are important. They are subordinate to critical thinking, and in particular, to being open to and willing to test alternative ideas. And that's what we're doing tonight. Some of the modern tools in my bag of tricks are these that are needed to stimulate critical thinking. A hand lens, a field notebook, a compass, a pair of boots, stereoscope for those who still know what an aerial photograph is all about, a backpack. Essential is a little thing called a canteen, samples collected, good notes taken, and not but least one of the more important aspects of field work. Now, these parts of the Ruby-East-Humboldt complex, we've got this lower Ruby-East-Humboldt suite of crystalline rocks. We've got the myelinitic carapace on top of it, and we've got the Wood Hills suite. These are essential pieces to the story. We're going to go through the burial and metamorphic history and how these apply to the Nevada and Western Utah. Now, where do they occur on a distribution? Here, the red dots, these are where the crystalline parts, the lower portion below the metamorphic carapace, or the myelinitic carapace. The yellow dots are where we've got metamorphosed upper plate in particular. And here, these two places, you can walk from metamorphic to non-metamorphic rocks. Here in Lamoille Canyon, courtesy of Keith Howard, the mountain, what I call the mountain goat from Menlo Park, the mapping he did in here was incredible. But this is what this Ruby-East-Humboldt metamorphic complex looks like. Here's another picture. It looked like you're in the Alps, but this is spectacular work that's been done there. Now, the myelinitic carapace that separates the Ruby-East-Humboldt suite from the overlying Wood Hills. Glorious exposures. If you haven't seen them, you got to go visit them in Secret Pass or Lamoille Canyon. Here's Lamoille Canyon, and here's Secret Pass. We'll look at them right here in Secret Pass. Myelinites, the most beautiful myelinites I think you'll ever see, from ultramafic to porphyroblastic myelinites. It's in all their glory. And here are the same rocks, and this is not bedding, but this is the metamorphic foliation in the myelinites. Now, the Wood Hill suite up here. The Wood Hill suite is, to me, the reciprocal of the Ruby-East-Humboldt suite. It comprises regionally metamorphosed Neoproterozoic to Mississippian rocks, typical of the eastern Nevada carbonate myogeocline. Depending on the area you're in, the metamorphic rocks grade upward into non-metamorphosed rocks in the Ordovician in the Pequop Mountains, or as high in the section as Devonian or Mississippian in the Wood Hills and southern East Humboldts. A complete non-metamorphosed section from Ordovician continues to lower Jurassic rocks down in Curry from the area that we worked in the Pequop Mountains. Now, this picture came out much better than I had expected. This was taken in 1961 from a super cub just before I got a horrible case of air sickness. It looks like layer cake geology. Down here, we've got the upper Ordovician Poconet group. This right here, it grades from here down, from non-metamorphic into the metamorphic sequence, and on farther to the north along here, it gets down to the Prospect Mountain. On top of that is the beautiful Eureka quartzite. And then the upper Ordovician to Silurian Dolomite section. Above that, the lower Devonian Dolomites and the upper Devonian Gilmet limestones. On top of that, the Mississippian Chainman Formation, these shales. And that looks like good layer cake geology. But man, it's anything but that. What it looks like more in many places, looks more like the cake got dropped on the floor and got scooped up, and not in a very careful manner, and just got slapped back on the plate. Now, on top of these rocks, up here, coming across this, is the Ordovician Poconet group. that group right here. This is known as the Independence Thrust. And this is a major structure in this area. Now, look at some of the non-metamorphic rocks. Here's the upper cliff former of the Gilnet Formation. Beautiful looking rocks in here. They look like they're absolutely undeformed, but the worst thing you can do is get up close, because then you're in for a big surprise. Some of the beautiful preserved gastropods in the Gilnet, some fantastic stromatoporoids. If you've ever worked with these in the Gilnet, some of these things get to be the size of a bowling ball, and they weather out, and you think you're looking at these grayish white bowling balls on the hillside. Up above that are some Sabka zebra dolomites. So there's a lot of fantastic sedimentary stratigraphy here. Here's the dolomites, what they look like, undeformed. And here, from the Pequop Formation up in the Permian, is fusulinid-bearing limestones. These little blobs like this are fusulinids. And this is what they look like in cross-section. God's gift to understanding the age of the Pennsylvanian Permian. Now, a tertiary unit. This is one of the greatest places I've ever seen. This nice these bedded units look beautiful. Get up close and see what they look like. These are megabreccias. That is those are blocks of an Ordovician Cherty limestone, came flooding out in megabreccias. And these are quite common in the tertiary out here. Oh, and for this, if you want the second half of quarantine, this might apply to some of you. I know it does get a little old being in the house with your family. You didn't marry for 24 hours, just for part of the day and a night, and that's about it. Now, a look at some of the metamorphic features. Regional synchromatic and late tectonic to post-tectonic features. This is a lower Ordovician Lehman limestone. You can see the lineation in it. This has gone through quite a bit of shearing and sublineation, and in the argillaceous intervals, the argillaceous rocks are slightly micaceous. This is up near the top of the metamorphic suite. Below that is the Kanash Shale, which now is a biotite phyllite. Down lower, you get these marbles, banded marbles, metamorphic segregation, light and dark, from what were originally medium to dark gray limestones. And in some places in them, you see little stringers like this of chert floating in there. And you can see the metamorphic banding here. And then the most beautiful rock in all of this is, to me, the Meta-Dunderberg Shale. It's lowermost upper Cambrian in age. This came out of the Wood Hills, and it's a biotite, muscovite, andesite, garnet, starlight, kyanite schist. And it's one of the rocks that has contributed to this idea that these rocks were buried at least 20 kilometers to attain this type of metamorphic rock. Now for the post-tectonic to late tectonic, here we've got this little rosettes of tremolite along the bedding plane. That didn't happen during penetrating deformation. That's either late tectonic or post-tectonic. And in many of the metamorphic rocks, we will see poikilolytic biotite that cross-cuts the foliation defined by the biotites, the micas. So we've got a post-tectonic to late tectonic to post-tectonic phase of crystallization here. Now, one of the best parts, these arrows are, this is the Dunderberg Kanash Shale again. These are biotites. Here's some more. These little arrows are pointing to well-preserved biotites that are replaced by graptolites. I mean, these are well-preserved graptolites replaced by coarse-grained biotite. And Larry Snee has dated these as 70 MA graptolites. the world's youngest graptolites. And if you know anything about graptolites, they never got this far to the tertiary. But anyway, this is one of the ways we can tell without question, regardless of the stratigraphy in the metamorphic rocks, by fossil evidence, we can tell you exactly the age of the rocks in this metamorphic suite. Now look at some of the types of structural deformation that we see in the Pequops. Folds, bedding parallel faults, and thrust faults. Sometimes bedding parallel faults will be called attenuation faults. They both do they're the same thing. It depends on whose vocabulary you want to follow. But I'm going to show you some deformed rocks that you wouldn't expect to see when you look at it from that aerial photograph I showed you. This is a limestone between the two largest thick-bedded limestones at the top of the Guillemette Formation. The overall unit, these folded rocks in here, are between undeformed, massive limestones that are dipping off to the right at about 30 degrees. I walked up the mountainside, and then when I came down, I looked over on the hillside, I said, where the hell did that come from? And I climbed up on the hill on the opposite side of the canyon and took this photograph. Bewildering. You walk up the ridge line and you see almost none of this. You have to get just the right exposure, and all of a sudden you find out these rocks are not as simple as you thought they were. And in this zone, most of the deformation indicates top to the southeast. And for those who don't believe in bedding parallel faults and attenuation faults, I got news for you. Look over here and look over here. You would never guess that this was right in between. It's wiped out this little bit of interval in here, and here these beds are nice, concordant here and there. If all you saw was this left-hand side or the far right-hand side, you would think this was just beautiful, undeformed, touched rocks. Look at that. I mean, Chris Henry and I happened to wander on this just out of the blue. I looked over and said, God, look at that. Here's another one. Look at this. Little thing stepped down, cut out this unit that was right here, and over here on the far right and far left side, there's nothing happening. So you think. But this goes on all the time. And if you get good enough exposures, this becomes a very common phenomenon. Now, when you get down low in the section, that other part was up in the Permian in the Pequop Formation. And some brittle folding and folding like that is common up high. Now, down low in the Ordovician Silurian Dolomites, here is a bed that just got ground up something fierce. And you could trace it along. It's between beds. This kind of phenomena you would never guess from an airplane. Connie Nutt and I mapped the exact same thing, same type of structures along the Nevada state line in the Goshute Indian Reservation north of Wendover. We could trace a bed like this for hundreds and hundreds of meters. And here they had beautiful rocks above and below it that were undeformed. Now, this is an old photograph. You can tell that's my field vehicle from 59 to 61. That's US 40 at the Pequop Summit in 1961, looking northeast. But look at those structures in there. My God. Tri-Pound Pass, at the time I called it Joanna Limestone because Joanna was the only name that existed at that time for lower Mississippi and Kinderhookian rocks. We had Tri-Pound Pass hadn't even thought about. And the Chain and Shale over here, the Blackute rocks. But look at these bloody faults. You look at the ground up behind it, the slopes, you would never find that. You would never find that. Now, another place that's a little bit deformed. Here's the Ordovician Pogonip limestones. Here's the Mississippian chain underneath it, and there's the fault. And here's the folding beds, drag along that. Top to the southeast. This happens to be the eastern extent of the Independence Thrust as it's come over from the top of the range on that you saw on that photograph earlier. So with all these structures, here's another type that is even more baffling. Here's an east-west high-angle fault. It's capped by Eocene volcanic sequence. There's some thrusting in here between Triassic and Triassic, but right across this fault is Devonian western facies. We have Triassic of what you might call the typical eastern carbonate facies rocks, and you've got the Devonian western facies rocks juxtaposed along a high angle fault. This is a tear fault in the system. And what's very important is these faults are very deep structures. During the earthquake in 2008, we came out to look at this area here again. And the focus of some of these faults we mapped here in the Oxley Peak Quadrangle north of Wells, the focus of these on this is clear down to as much as 15 kilometers. So these are not the simple superficial detachment style faults that we're used to seeing, although they may have been used by it subsequently in the Cenozoic. Now, are we wandering in the wilderness? Well, now to the question of the proposed deep burial of the northern Pequop Mountains to account for interpretation of burial to 20 kilometers for the regional metamorphism of our Neoproterozoic to Ordovician rocks based on geobarometry calculations from the metamorphic mineral assemblages. Okay, back here is Wells, the East Humboldts, the Ruby Mountains, the Wood Hills, and the northern Pequops. This red line is where the cross-section you'll see in a moment is for the proposed southeast directed Windermere thrust being rooted out in this area somewhere to cover this, somewhere on the order of 69, 70 kilometers. Here's that cross-section. But first, we have to take it apart because this independence thrust is a post-metamorphic thrust. So bring this back down to here, and they would put this whole section, 10 kilometers rock, on top of this lower part, which is metamorphosed just down here in this lower part. Now, how the heck do we figure out what happened? Well, conodonts are the solution. And what the hell good are they? They change color with increase in temperature dependent on how deep they've been buried. And what are conodonts? Well, they're teeth that came out of a mouth, teeth like this that came out of the mouth of a soft-bodied animal. It's, they describe it as maybe a worm-like or eel-like critter. And the fossil parts that we see are just the teeth that are left over. And they range in size from anywhere from less than 100 microns to as much as 12 millimeters. And these conodonts survived clear to the end of the Triassic. Now you have to study these under a binoc microscope, a damn good one. And the worst thing you can do is sneeze while you're looking at them because you've just lost 4 or 6 hours worth of work. They go like dust. Now here is in place conodont teeth here from a soft-bodied animal. And here we've got all of these teeth. They're all from the same animal. This tooth isn't from one animal, and this isn't from another one. They're all from the same specimen. And here are the different types of teeth that fit in the mouth. Kind of gross looking in a way. And if you dissolve these things in glacial acetic or formic acid, you get them out real clean, and this is what the conodonts will look like. Now, The solution is called color alteration index. As these conodonts are buried, they heat up and they change color from clear or cream to yellow brown to grayish brown to black. And then after a certain point over 480 degrees, they start turning gray and white and clear again. But at this point, they go from a lustrous texture to a cryptocrystalline texture, which is easily recognizable under the microscope. And here you see the range of how these can overlap. So you'd say, how can you get a 5 and a 6 together? Well, they can have overlapping temperatures, just like in here and here. A 2 and a 3 can be found in the same unit. Now, I'll show you some examples of conodonts collected. And these that I'm showing you range from 1 to 5.5 to 6 from the Pequop Mountains. And the numbers associated with them have two colors. One is green for numbers that give us CAIs, burial numbers, and one with reds are conodonts that have been altered. So here's a 1. They're clear. Look at the edge. It's hard to tell where the edge of that conodont is. You look at these little things out here. You can't see it, but now you can see this part. And that's because this is thicker. And it's as if you took about 10 layers of very fine grained, very light gray paper that was translucent. And you put them on top of each other. It would look dark. But if you pulled one piece out on the edge, you would see the true nature of that translucent paper. So here now, we've got a 2.5. Now look, these all of a sudden become quite visible. And this part is getting darker, but still out here on the edge is what you're looking at. And then here's a 3.5. It looks black, but really look on the edge. It's not black. In fact, in this one, you can see growth rings around the edge of this. It's so translucent in part. Now this dark material is organic carbon that's being changed. Now the next one, this one has a CA of 5. That's getting bloody hot. It looks, under the microscope, it looks like vitreous anthracite coal. It's that dark and lustrous. But look what happens when you exceed that. Now we're a 5.5 to 6. And the surface of this isn't lustrous, it's now cryptocrystalline. So what you're looking at is the ability to tell whether you're looking in the upper part of the temperatures. If you found this one right here, whoops, let me go back. If you found this one associated with this one, you would know that this one has been altered and there's something going on. Now here's a particular area, and I'm using the same colors, green for burial and red for altered. Here's a section, here's a scale of 1 mile where I've collected. I've got a 4, and this is Devonian Gilmet, Upper Devonian. 4.5, a 4, a 4, over here, a 5.5, with a little bit of an overprint on it, a low 5 here up in the Mississippian Chain Shale. Over here in the Mississippian Tripon Pass, look at it right next to this 4. Whoops, don't use that, stupid. This right next to it, with just within a few meters, I collected another one, and I got a 5.5 to 6, and another 5.5 to 6. Then up here, a 5.5 and a 7, 5 and a 7. Now, working with Charlie Sandberg, the expert in conodonts, I did not give him these things in order they were collected. We randomly looked through the sample numbers. And he looked at a couple of these and he said, Chuck, where the heck did you get these? These have been altered. And we put them all together, and gosh almighty, they make sense like you can't believe. Everything fell into place. Now, looking at the Pequops, 2 quadrangles that we've mapped. This shows the locations of most of the conodont samples that we've got. The area we were just looking at is this area down here at the south end, just off the map, where those are clustered. You see, we've got some altered ones in a variety of places. There's been a bit, and this is attributable to penetrating deformation and a little bit of calcite veining or silica veining in these areas. And all of a sudden, these things got a little bit of, if you will, for a better name, hydrothermally altered. This one right here, this is at the base of the Ely limestone. We got one, this one should say a 1, but this program won't show both numbers at the same time. And here we've got an altered one that's 4.5, and we're right next to a big fault. So that's very understandable. Up here, we go from a 3.5, a 3.5, to up here in the same interval, it's showing up the red one, a 5.5. This one right here, this green one would show a 4. This is at the Devonal Mississippian boundary. All the way along this whole range, we get the same numbers at the Devonal Mississippian boundary. We get higher in the section and look at what we've got, light, smaller numbers. We get up to the top, here up in the upper Pennsylvania, we've got a 1. It says it's never been buried. It couldn't have been buried. Now, where do you get these bloody little buggers? You get them out of, I got these out of many of them out of the basal inclinite at the base of the Tripon Pass, Kinderhookian age, where it rests on the upper Gilmet. This is maybe 2 or 3 feet from the top of the Devonian. A CAI of 3.5, just like we see everywhere along this contact. Now, here's a reconstructed section from the Triassic down to below the Cambrian, right here. Here's 10 kilometers, 5 kilometers, and so on. One thing you have to understand, when I showed you all those structure examples of the bedding parallel or attenuation faults, etc., you have to remember that no matter where you measure a section out here, it's not going to be the real thickness. Based on what I've seen, for the most part, you're going to see less than what the normal section was. This attenuation faulting, bedding parallel faulting, is very important. But at the same time, we've got some folds. So maybe they're making up for it. But the important thing is we look at these thicknesses and we look at the ranges around them, and they're pretty comparable from one range to another. So we feel that this vertical section is representative. Now, I'll show you where the CAIs, and sometimes I slip up and call it a CIA. That's another problem. But the CAIs, 1 to 2 in the Pennsylvanian Permian, up near the top, 1 to 2.5 at the base, and one of them that's altered at the base along the fault where I showed you. In the upper Chainman Shale and the upper Mississippian, a 3, another 3. The Devonal Mississippian boundary, the base of the Tripon Pass, 3.5, a 4.5, a 5, and a 4. And then we've gotten some 5.5s up to 7 of altered ones at the same area. And that's because this interval between the Tripon Pass and the Gilmet and the Tripon Pass and the Chainman Shale is a very favorite décollement, or whatever you want to call it, a bedding parallel fault. There's a lot of deformation as you go along here. Now, down farther in the Gilmet, a 5s and a 4.5 and 4s. Down in the Silurian Roberts Mountains Formation, from 2 very isolated areas. They were in fault blocks about 1.5 miles apart or so, both 4.5s. The Kanash Shale in the Pequops, a 5 and a 4.75. And from that same unit, a 5, a 5.5, and a 6, altered. So what we can say with considerable confidence is that this is a normal stratigraphic section from the metamorphic rocks down here, down here, all the way up. The metamorphism dies out in this interval right here. This is the Eureka quartzite, and away we go. Everything fits. Now, what happens from here? I'm going to show you a cross-section from south to north in the Pequops. I've got Permian Pennsylvania CAI of 1 up here, and a Permo-Triassic CAI down here to south. In the middle, where the range, up high in the middle of the range, Upper Devonian, 3.5 to 4.5. Let's see what that cross-section looks like. From north to south, 65 kilometers. At the north, we've got these Pen-Perm CAIs of 1. They've never been buried. And that geology can be projected all the way across. And here we've got the Devono-Mississippian boundary of 3.5 to 4.5, paralleling that same line. And down below it, right here, we've got CAIs of 5 to 6, 5.5 to 6. Again, just what I was showing you previously, a normal progression from metamorphosed to non-metamorphosed to never buried. With this relationship, we say it's impossible to bury the metamorphic rocks more than 1 normal stratigraphic depth. Now that takes us back to this cross section. If you put this up over here, let's look at what I just showed you. Here we've got the CAI of 1 in the Permo-Triassic down to a 6 down here in the Cambrian, Upper Cambrian, Lower Ordovician area. So we've got a normal progression. If that's the case, you can't have these rocks on top. You cannot. Now look at what would happen if the Windermere thrust had existed. We would have a CAI of 1 here, a CAI of 6 here, like that. We would have a CAI of 7 or so down here, and down below 9 or higher. That would be the normal progression with temperatures under a normal burial condition. And that is not what we've got. So let's look at that section in a different way. Depth of feet and kilometers. As we go down, we go from clear to cream to pale yellow to dark yellow, brown, brownish clear to black at this section with what I just showed you. If we did like I just showed you, put that on top. Now, these rocks would have to do this. They would have to be black here and progressively go to the gray to where the conodonts would get completely altered. And that is not the case. So we rest our case that the Windermere thrust could not have existed. So as one of my friends would say, where did you put them rocks? Now, let's get to a regional picture. This metamorphism was initially late middle Jurassic to early late Jurassic in age. We have a Pluton over at the Silver Zone Pass, just a few kilometers off to the east, that cut metamorphosed lower Paleozoic rocks. We've got Lamprophire dikes in the Pequops that are almost assuredly 160 plus or minus, like all the rest of them in northern Nevada, that intrude these independence thrust, what means the thrust is pre-160. So the metamorphism has to predate that because that thrust fault is post-metamorphic. Now, we've been hit in the Sevier and up into the Cenozoic by any number of subsequent very high geothermal events. And let me tell you, it's reset the clock. The KAR numbers from the Woodhills and the Pequops do not show Mesozoic, but they do show the rocks that give the ages up in here. They do indicate that something was there before that. Something's been reset. But the nature of the beast is we can't tell when that was. But if we go by some of the other data, we feel pretty good in saying that that was here. And the other part is the late tectonic to post-tectonic biotites and whatnot, again, have been hit by these thermal events, and we can't tell if that late tectonic to post-tectonic was Elko age or Sevier age or Cretaceous age. I mean, Cenozoic age. That's one of the problems with some of this thermal reheating. You destroy the time clock, you reset it. Oops. Now to this picture. Here's what we've been looking at. Here's the Nevada-Utah line, Wendover, Elko, about 150 kilometers, the Ruby East Humboldt Range, the Wood Hills, the Pequops, etc. Ely, give you an idea. Now, what I'm showing you here is CAIs in the Triassic throughout this whole area. Look at them. They're 1 to 2. Here, there's some contact metamorphism problems in here. But you look at things, that says that all of the ranges, all the rocks that underlie that we see have never been buried. This area has never had a major thrust sheet bury any of these. That's very, very important. Next, we were looking at this. Here's Elko, Winnemucca, Las Vegas is down here, Ely. Look at this area. This area has never seen a temperatures greater than about 140. These are all Triassic. Here, look at them. Here's a 3, here's a 3.5, but look at the bulk of these. That tells you that this entire area, in my book, these rocks have never been buried. They've all remained at their, more or less, their stratigraphic depth. So what does that do to us? Well, if you want to do crust shortening of the rocks, you take out the tertiary extension, and let's leave this line steady. Sure, you can do 25, 35, 50%, whatever you want to do on reconstruction, 100%. Well, if you're 100%, you're here. That kind of hurts. Over here in Utah now, we do have older over younger major thrust faults. And depending on who you talk to, these may have accumulated shortening of 150, 200 kilometers, depending on who you want. But if they take out tertiary extension, that may bring them back to here. But still, you have to get rid of that overthrust shortening. That means you bring, let's say if it was to here, you bring it over to here. What happens to these rocks? They've got to move west. In other words, what I'm saying is all of these rocks, somewhere deeper than we can see, we've ever seen, this is all allochthonous. And it all belonged farther west. So that'll give you something to constipate on. Now, I just want to thank you for putting up with this. Hopefully you had a better grasp of the geology of the region, and most likely better than I do. Now it's time for drinks, and maybe you've already started to drink much earlier than I did. But anyway, go for it. And Mike, take it over.
Okay. Well, thank you, Chuck. I think the first thing I want to do is just congratulate you, Chuck, and I think everyone else wants to do the same. That was a fantastic talk, and definitely something that is regional in scope and of a lot of value, so thanks. Chuck, if you can, you should be able to take off your share screen now, and then we'll go into the question mode. Oh my God, your desktop is worse than mine.
Well, we're not going to show that, for God's sake.
Oh, that's even scarier.
Well, 6-bit place looks a hell of a lot better than mine.
Yeah, we could just keep everyone muted, Chuck, and then you don't have to worry and get away scot-free.
Yeah.
You want to do that?
Well, whatever. I'm up to anything. What's been nice is you've muted everybody so nobody can say anything while I was talking. That's better than a live talk where people stand up and get out, tell you, you know, give you these real friendly hand signals and whatnot.
Yes,
But
the timely
this
coughing and
this is
gagging.
great. But I'm open to a Q&A session, no problem.
Okay, well, let's go for it. Everyone, you have a chat icon at the bottom of your screen, so use it. Just send a group
Well, not
chat.
everybody, not everybody, good God.
Well, everyone who has a question can use that icon to ask a question. And I think if you ask the question on chat, I'll pick it up and just repeat it to the group if that works for everyone. Another alternative is to use the raise hand icon, which I can't see, but I guess you guys can. And you can raise your hand. It's another icon at the bottom. And I think that automatically unmutes you and you can then ask a question. So with that, do we have questions? And use that chat function. We've got to have a few. Okay, we've got some here.
Maybe they're being polite, which is not normal for geologists.
Okay, I'm just going to take these in order. First one is from Paul Dockweiler. How do we learn more of this? Let's see. How do we learn more of Conodont geomorphology of Nevada? Is there a paper that we can consult to find out more?
My God, there's a million papers. Look up Charles Sandberg, Barney Poole, Anita Harris, Bruce Wardlaw. These people have done literally thousands and thousands of conodonts in the area. Barney and Charlie in particular on the maturation problem for the oil companies, looking at throughout central and western, central and eastern Nevada and western Utah. Their work is legendary. The problem with too many people now is they don't realize there were some papers written back in the last century.
Mm-hmm.
And a lot of them, the best ones are in guidebooks, which sometimes gets to be difficult to dig out. But Barney Poole and Sandberg are your best bets now. Those are the only two guys alive out of those four that I mentioned. And that's, thank God for that, because Charlie was a godsend for doing this work.
Yeah. Well, it's great to have tilted sections that are exposed like we have in Eastern Nevada, like in the Pequops. And I think you were one of the first ones to note that, there's this general progression from unmetamorphosed upper Paleozoic rocks into moderately metamorphosed and then severely metamorphosed lower Paleozoic rocks.
Well, for the last 4+ decades, I've sworn up and down to people that that area could never have been buried, because in the Spruce Mountain, on the west side of the Spruce Mountain, the Pocono grades up from metamorphic to non-metamorphic. The same thing in the Pequops. How in the world can you put anything on top of those rocks? If there was anything on top of them, they've been eroded off, and the valleys would be higher than the bloody mountains. There's that much rock you have to get rid of. It just doesn't make sense. That's just my 2 bits, which isn't worth much to some people, but that's great. 2 bits isn't worth much now anyway. Well, it is now for a little bit for gas, but it won't be in another month.
Okay, we have another question from Stuart. He says, can you expand on the attenuation faults? Is there evidence that they thin the stratigraphic section, and if so, how much?
Oh my God. You look at it on an outcrop scale, you know it's been thinned. But the guy who made this really popular was Lehigh Hensey over in western Utah when he was running field camps. He had students measuring parallel ridges, measuring the section. And they'd come back and he'd lay them side by side. And he said, you guys are nuts. Can't you compare one place with another? Look, you don't have the shale that so-and-so has over here. And this guy over there says, you don't have this other shale. So he went out with them every day. And every one of them was right with what they were mapping. No shale here, the guy on the next ridge. And all of a sudden he realized that there were high angle tear faults between these, going down the gullies between these ridges. Mm-hmm. And every one of them had mapped correctly. But the shales were getting squeezed out here and there. And his one thing to Connie and me. When Connie and I, when we went to map in the Drum Mountains, he came out and he said, look at the skyline ridge of those big limestones. He said, if they're going across without any options, without any breaks in them, you can feel pretty sure that there's not much going on below them. But if you look up there and you see vertical fractures here and there all along through there, he says, you better be careful that something's going on in the rocks below you, because there are probably high angle tear faults going along here, east-west faults, and you're going to find out that you're encountering what he's called attenuation faults, and buddy, you're in trouble.
Okay, well, this is a related question. Are you ready? This one from Jason Price says, hi, Chuck. Are the attenuation faults a product of the Elko orogeny?
They're a product of every contractional deformation out there, starting with the Roberts Mountains with the antler orogeny, the Humboldt, the Sonoma, the Looning Fence-Maker, the Elko, the Sevier. All of these are basically southeast directed or easterly directed. And we've got tear faults in all of these. And it's a common phenomenon in tectonics.
So maybe true, but very, very difficult to date.
They're really, well, they're not nice.
Okay, we've got another question, this one from Jonathan Price. Why was the geobarometry wrong? And multiple types of geobarometry, apparently.
Geobarometry, there's a paper in July of 2014 in Geology by a guy named John Wells. And he pointed out that theoretically, and I believe what he was saying is that metamorphic rocks and igneous rocks cannot be considered the same when you're doing geobarometry. Metamorphic rocks are formed with both lateral stress and lithostatic pressure, vertical. You've got two effects that are going on. In igneous rocks, you can use basically lithostatic pressure. And if you use the same concept, and if you add, without knowing it, the lateral stress that the metamorphic rocks are putting on there, you're increasing the lithostatic pressure in your calculation. And he said, if you're off by half a kilobar in your estimation of the geobarometry of a metamorphic rock, you can be off 10 times that much in the actual burial. And 10 times that comes out greater than 15 kilometers. That's a big problem. And when you get to looking at metamorphic terrains around the world, you see all these gigantic numbers for how deep this terrain was when it was metamorphosed. But in most of those, you can't reconstruct what was on it during metamorphism. So you accept these huge numbers. Yeah. And in my book, I would be very suspicious of them. Let's just put it that way.
Yeah, we've got some information from Chris Henry on Paul Dockweiler's question about references for Conodont studies.
Yeah.
Professional paper 995, Paul, if you're still there, is an excellent summary of Conodonts and their CAIs. Anita Hill did a lot of work working in the Great Basin on Conodont CAI maps and interpretations. And so you can reference that professional paper, which is probably one of the best ones, if not the best one on Conodonts.
Yeah, well, that's the paper where she pointed out what CAIs are and whatnot. Mm-hmm. But there are two guys that are still alive. Charlie Sandberg. Charlie, I hope you don't kill me. But his email address is conodonts at comcast.net. And Barney Poole's address is barite at comcast.net. And these, to me, these are the two guys who are the real pros in this game. And they can put you onto all kinds of stuff, more than you'll ever want to read. But they are the pros in understanding what's been going on and using conodonts for structure and stratigraphy. And structure, Bruce Wardlaw, long time ago, worked with J. Fred Smith up in southern Idaho did Conodonts for J. Fred Smith and found out the two fault blocks juxtaposed, same age rocks, had completely different CAIs. And there was a structural picture that came out immediately that something has happened in a pretty good way to get these two different CAI groups together. So it's a great structural structural tool.
Yes. Another reference that Chris brings up is Wheeler 2014 in Geology. This has to do with the effects of stress on rocks. And so
On metamorphic rock. Yeah, that's the one I mentioned. Geology 2014, July. And there are two papers in there by John Wheeler and another fellow who talks about the Barovian rocks, but that's right.
Yeah, so it might not just be strictly a burial effect, but we also have stress related to shear stress that can impart, I suppose, metamorphic effects on rock.
Yeah. It's great sport, and Chris put me onto that, and that's why I got started on these Conodonts out there. So it's all Chris's fault.
Okay, any other questions here? I don't see any on the chat.
I see 16 listed there. I don't know. There's another one.
Yeah, I'm going to unmute everybody, and I don't know what that's going to do. I think it'll be just fine.
Well, we might hear some unusual. Well, not.
Is that good? Nope. Sorry about that, Chuck. I had you muted.
You have to do that. But anyway, what happened is all those that replied, the most important thing that they pointed out was boots on the ground field geology. That is what everybody was talking about, whether it's academia, the industry, or government. This is the most important thing we can do. If you don't have a good geologic map, you don't know what the heck to do with your samples.
Hey, Rick, are you on there? Rick Redfern? Can you hear us? Let's see if I can unmute you. Okay, Rick, you have a question.
Yeah, I'm here, yes.
Go ahead and ask your question.
Yeah, hi, Chuck.
Hey, Rick.
We were out on a field trip with Keith Howard a year, maybe 2 years ago, out in Lamoille Canyon.
Yeah.
And in the north central part of the canyon, you look on the east side, and way up high on the top, you can see these. It's a flat, well, semi-horizontal zone, but big isoclinally folded rocks in it.
Yeah.
And, have you ever seen that? And do you have an idea what is it, a Decolamont zone way high up there, and what orogeny maybe you would fit in with your stuff?
Oh yeah, I saw those back in 61 and 62 and 4 when Keith was out there. He did some of the most fantastic mapping that's been done out there. But there's no question that these are recumbent folds, and they have to be, in my book, Elko age and or younger. And this is a soupy basement that was going on, and the Woodhills, what I would call the Woodhills Suite, and the metamorphics at the base of it were probably metamorphosed during that. But they somehow or other, that sequence has been detached along this myelinite zone. Although that's my opinion, but no one has seen a contact between the Ruby East Humboldt and the Woodhills Suites. Nobody. But I concur completely with what Keith Howard has done out there. It's a spectacular job.
I asked Keith whether he thought it was severe age, and he said, yeah, that's a good possibility. So
That's a good statement. And I exactly what he said is right.
Chuck, I think Larry Snee has a question for you.
Oh my
Hey,
God.
Chuck, how you doing, buddy?
You're still awake?
I'm trying to be. I'm out here in Florida. So one of the issues you showed before that there's been much displacement along bedding parallel faults.
Yes.
How much do you think?
You don't see them?
No, I see the faults. How much displacement has there been?
That's the $64 question. Individual ones maybe a few meters to tens of meters, but when you start looking at how many bedding surfaces you've got over a 10-kilometer section, and if this is a fairly common event, the top could have moved a long ways in relation to the bottom. And that's a real problem. I don't know anybody that can answer that. It's just, we could have tens of kilometers of, well, no, I'd say maybe several kilometers of displacement between the top and the bottom to the east or southeast. I don't know. I don't know how you do it.
No, yeah, it's a good question. How do we figure out how to solve that problem?
I don't know how. Now, unless you can get an excavator and cut across it and clear across a mountain range and want to measure every one of those damn things all the way from top to bottom. But then you'd just be guessing.
Yeah,
but it is an important thing to understand. When I was doing my thesis in 1960, Clark Hose and Dick Hose and Clark Blake came out and visited me. And I can't repeat what Dick Hose said, other than to say, my God, you've got a lot of bedding falling in here.
Yeah.
And John Welch said the exact same thing, up higher up in this section. And if you haven't moved the map out there very long, you really don't realize how widespread it is, both vertically and laterally.
Yeah, and the other part of this is because of the geobarometry.
Yeah,
there's been an attempt to thicken the crust.
Yeah,
maybe there's been attenuation of the crust, thinning of the crust.
Yeah, but God almighty, you're going to take 10 kilometers out of it? I don't think so. That would be that the crust is now half as thick as it was then. That this section has been cut in half. I can't buy that.
Okay, that's fine.
Okay, go back to sleep.
I will. Thank you.
Okay, any other questions for Chuck? We've got one from Art Snoke. Let's see, where are you, Art, on this list of?
Oh, he's up in Laramie.
Are you Arthur? No. I want to unmute you.
Now, one thing you have to understand is these depth of barrel things have nothing to do with the Ruby East Humboldt suite. That's a whole nother ballgame. I'm only talking about the stuff above the milelite, the Woodhills, Pequops, and that type of stuff. I'm not talking one iota about those other rocks. I don't want to get involved in them.
Yeah. Just a quick question following up on what Larry just said, though. You know, there are all these little faults that you talk about, or attenuation faults. Maybe they're small contractional features, but they're not adding up to lots and lots of thickening of the crust.
Well,
and they're not adding up to much thinning either.
That's exactly right.
You're pretty much saying they're inconsequential.
In the overall thing, it may be status quo. Who knows? That's very hard to say. We don't see it, but we see enough to know that both are going on. And how to calibrate this numerically is impossible. Because if you do it, you're only looking at a couple of formations. You're not looking at the entire section. And I don't think anybody has a lifetime left to do that. I know I don't. I don't give a rip about the rest of it.
Okay, Art Snoke has a question now.
You got him?
Art, are you on there?
Can you hear me?
Yeah. Go ahead, Art.
Okay. Hey, Chuck, I wanted you to talk more about the boundary between the Tripon Pass and Gilmet Formation, where you have a lot of hot conodonts along there. Is that a detachment fault or attenuation?
Well, in places it's a detachment fault. Yes. No, well, no, not a detach. Excuse me. No. It's a bedding parallel fault that off and on cuts out the And in other places, it's all normal. It just depends upon where you are. And that one place where I showed, all those samples, there's a high angle fault goes across there. And on one side, the unit's 150 or more feet thick. On the other side, it's about 15 feet thick. So there's this tear fault that's taken place during Mesozoic time at some point, I don't know when. And there's been slip along the bedding parallels movement along the top and bottom of the Tripon Pass. But I don't believe that that's a detachment fault in itself. It's well within the entire section. And it carries everywhere, all the way from the north end to the south end of the range.
Well, what's the reason for those hot conodonts in there? Is it just fluids?
Yeah, because where I find them, the limestones are folded and faulted and crackled and whatnot, and there's a lot of calcite veining through there. So it's obvious that there's been fluids moving through there. If I get away from that, I don't get these anomalous numbers.
Okay. Okay, thank you.
Any other questions for Chuck? Okay. Well, Chuck, I guess you're going to get away with this today. Oh, there might be another question.
Oh, gosh.
Oh, it's Dave Reese. We're onto this attenuation faulting business still. So let me find Dave Reese in the list here. There must be an easier way. Okay. Dave, how's it going? Can you hear us?
You're going to have to get replaced there, Mike.
Dave, are you out there somewhere? Okay. Dave says he doesn't have a mic.
Oh, that's too bad.
Okay, so here is his question. Let me make sure it's a question. It might be a statement. It says, bedding parallel attenuation of likely Elko age played a significant role in the formation of the geometry of the Long Canyon deposit through megaboudinage. And so Dave worked for at least one field season, maybe longer, at Long Canyon during the time that Frontier Gold had the property prior to Newmont and the mine being put in. So did quite a bit of detailed mapping throughout the district.
Yep. And I've seen those things. I've seen their sections and everything, and that's absolutely true. I think they've done a spectacular job in there.
Yeah, just a lot of questions from various people, similar to the earlier question about why the geobarometry led us wrong here.
Well, the geobarometry didn't lead us wrong. It's a matter of understanding how the geobarometry was calculated.
Mm-hmm.
The people that did that work did it very accurately. But we've got to improve the way in which it's reported. That's all.
Yeah.
I don't think those people should be criticized at all. That's not fair. That's not fair.
Following up on Art Stokes' comment about what's so special about the Tripon Pass Gilmet contact, Chris Henry says the Gilmet, Tripon Pass, or Island Mountain, or Joanna, whatever you want to call it, for all its facies, is extensively, altered hydrothermally throughout much of north central and east central Nevada. So it's a favored locality for hydrothermal fluids to have migrated along. Fundamental break.
Yeah. Well, let's put it this way. And Charlie, you may want to come on and correct me, but Charlie and Barney have found that the Devono-Mississippian boundary throughout central and eastern Nevada is about the same. There's 3.5 to 4.5. So it's a widespread, within a narrow area, narrow span of temperature, the same everywhere, unless you've been altered.
Yeah, that's certainly true down around the latitude of Ely and Eureka, Nevada, where there are a lot of Carlin-type deposits that are hosted at that same contact. And then the southern Carlin trend as well, that Chris points out here. Lots of fluids being localized along that. Devonian Mississippian contact.
Yeah.
Okay,
Well,
other
Yeah,
questions?
well,
comments
the
for
thing
Chuck?
is, with the Chainman Shale right above it, and the massive limestones below it, it's a favorite place. Big contrast in rheology, and when you've got contractional deformation, that's the kind of place you would expect to break first.
Yeah.
So to me, that's a normal occurrence.
Well, very good. I don't think we have further questions unless someone has one real quick. Chuck, I just want to thank you again. That was a most entertaining talk and very informative and far-reaching, I think, in terms of its breadth of geologic concepts for Eastern Nevada.
Well, what I hope it shows is that field work is precious, and it's very important. It's the most important aspect of any project.
Yeah.
And how you collect the samples. And that's the way it is.
Mhm.
And
All right, then.
my undergraduate professor told me when I was working on my master's, he said, Chuck, you don't think you understand that? I said, don't worry about it. Just keep mapping. Don't try and understand it all at once. Keep mapping, and pretty soon it will all come together. Don't get excited about it. Go out and have a drink once in a while, but don't get excited about it. And I found that that's worked. And if it's really complex, get the hell out of there, circle the wagon, and map it in from all other directions. And maybe you find out that complex area isn't so bad after all. But that's mapping.
I agree. All right, everyone. Well, thank you very much.
Okay,
And,
well, thanks, everybody. I appreciate it.
Yes. Thanks very much, Chuck. And for everybody who's still on, we're going to continue this virtual series of symposium talks. Some of these talks, Chuck's was a new talk, not planned for the symposium that never happened, but some of the talks will be talks that we had planned that are somewhat of a timely nature for the 2020 symposium that couldn't happen, obviously, and so we'll have various folks get up and give their spiel, and this will lead all the way up to May of next year when we'll have the actual symposium, hopefully. So thank you very much. Stay tuned.
Yep.
Watch your GSN emails for further information on future talks. And Chuck, I just want to thank you today. That was good.
Yeah, and I'd like to ask one thing. I see Paul Lincoln's on there. Paul, if you'd contact me, I'd like to talk to you. You poor joker.
Does he know how to contact you?
Well,
You're giving out everyone else's email address.
cthorman@comcast.net. Well, it's in the bloody
the directory.
membership. It's in the membership directory.
Exactly.
Yeah, and send
Pay
checks.
to be a member.
I accept checks, no problem.
All righty then.
Okay, take care. Thanks, everybody. I appreciate it.
Good night.
Good night.
Hasta luego. I'm going to call SIG right now.
Okay. How many people are still on? We still have a lot of people on. Chuck, did you want to talk about anything?
Well, I guess I better get the heck off here. I'm out. Goodbye. Thank you.
Good night, everyone. Take
Good
care.
night.